So I'm going to talk to you about merging neutron stars and black holes and some of their electromagnetic signatures of them. We have a reminder of some of the context here that we've seen in one event already, multi-messenger signatures of gravitational waves and electromagnetic radiation in this binary neutron star merger of 2017, where we're seeing across the electromagnetic spectrum in gamma rays, X-rays, radios, but also UV and optical emission over periods of days and weeks, which I'll spend most of the time talking about. This we think is the material that was liberated from the system when the neutron stars came together and became unbound, formed into heavy elements, and then powered a radioactive glow over periods of days and weeks afterwards. And that was certainly an exciting discovery. And the question is, what's next? What else are we going to find? What else are we going to learn from this kind of science? And so, of course, one thing is to find more of these events and see how typical this one was, and how common they are, and can they account for production of all the heavy elements in the universe. Another that I'll focus on a little twist of the scenario is the possibility of having, instead of two neutron stars merge, a neutron star and a black hole, because LIGO's now discovered several candidate events of this kind of phenomena where the mass ratio is high, and it looks like, in some cases, this 1908-14 event, there was a 20-some mass, solar mass object merging with a 2.5 to 2.7 solar mass star. These two later events, a little bit more moderate in their mass ratio. In this case, 5 to 10 solar mass object merging with a, something in the 1.4 mass solar mass range, right? And so these are nice candidates for black hole neutron stars. It should be said, with the LIGO data, we don't really have any direct evidence of what these components are, other than their masses, some information about their spin. There's constraints on how extended they can be, but those allow for either neutron stars or black holes. And so the reason these are nice candidates for neutron star black holes is because we think black holes may come in masses higher, in this higher range. It's not possible to get neutron stars with masses above a certain value, and that the lower mass object is sort of nicely in the range of a neutron star. But it'd be nice to get some additional evidence that these really, what the components of the system really were. And in some cases where we have a relatively massive secondary that's pushing the maximum mass we think that the neutron star can have before collapsing to a black hole. And it's trying to learn if this is really a black hole neutron star, or whether there's some population of lower mass black holes in the few solar mass range, and that these are just the other types of binary black hole mergers. And so that's where electromagnetic information can come in handy. These events, for example, the large mass ratio event in 1908-14 was observed by large numbers of groups through electromagnetic telescopes in the optical infrared, as well as across the electromagnetic spectrum. Huge amount of resources, and here's just one example. The system was significantly farther away than the 2017 event, so 200 to 300 megaparsecs, and in a larger uncertainty region on the sky, so it was much more difficult to try to find an electromagnetic counterpart. But a valiant effort was put forth, tiling a huge range of the sky, discovering numbers of possible transients in the region that could possibly be candidate counterparts, all of which were ruled out for various reasons, doing spectroscopic follow-up. In other words, discover that they're supernova or other sort of known transients. And so no counterpart was found, but it was interesting exercise to show it was possible, and to put some constraints on what might have been seen. This is just one observation data set from the Gravity Collective by Charlie Kirkpatrick, which they had upper limits on the luminosity of this possible electromagnetic counterpart in different wavelength bands. that basically showed that the event couldn't have been you know a few times brighter than the 2017 event, and tried to put some constraints about how bright the counterpart could be compared to certain models, and in a sense constrain the amount of matter that might have been ejected in the black hole neutron star. So that's the question that will continue as we go further. We had these black hole neutron star mergers. What would make them distinctive in their signatures from binary neutron star mergers? What might we see, if anything, that would tell us something about these systems and their possible contribution to the heavy elements? And the dynamics were thought to be somewhat different in these events, where a black hole, if it has a significant mass ratio, can actually tidally tear apart parts of the neutron star, send out some material in a tidal stream like this. Most of the matter will go into the black hole, but some amount will be held up in an accretion disk around the black hole. And this presents sort of a signature of the asymmetric mass ratio, the fact that we get this sort of one-sided tail from the neutron star coming out, whereas in a binary neutron stars of basically symmetric mass ratios, we'd expect to see a more, well, less massive and more symmetric tidal emission, as well as significant disk contribution. So just a few of the kind of questions we can talk about in this discussion. What are the signals of these electromagnetic counterparts, radioactive elements that are glowing after the merger, the so-called Kilonova event? And what might that tell us about, when combined with the gravitational wave data, some constituent, whether the constituents are black holes or neutron stars, maybe something constraining their spin, properties of the system like its geometry or inclination, whether these neutron star black holes are contributing to the R process, heavy element production in the universe, compared to the neutron star mergers. How do they relate to the equation of state of neutron star matter, particularly how it affects the radius and maximum neutron star mass? All right. And one question I will focus on a little bit in particular, because it seems to be asked a lot when I talk to people, especially gravitational wave people that work in this area, is given that the material that gets ejected in these systems can be highly asymmetric, is there any information there that would allow us to constrain the inclination of the system? As that is notoriously hard to do with the gravitational waves alone. There's degeneracy between the distance and inclination estimation from the gravitational waves, but you can can try to break within the gravitational wave data alone using some higher order effects. But is there anything in these systems in terms of the light curve, its anisotropy, its shape, the spectral signatures, or polarization of the light that we see, that may give us an independent handle on that and really kind of exemplify the joint value of having multiple messengers of these systems, right? And this is just one example for two of these black hole neutron star merger candidates, showing the estimates from the LIGO paper of the uncertainties in degeneracy between distance and inclination angle. One of the reasons that this is interesting, or something that you would like to know more about, besides just telling us more about the system that we're observing, is that it goes directly into potential application of these kind of events to measure cosmological distances and cosmological parameters like the Hubble parameter, since the uncertainty in the distance translates into your uncertainty in the Hubble constant. And so this was really one of the biggest errors in the LIGO attempt to constrain the Hubble parameter with the 2017 event. There's claims that if you add in electromagnetic data, that you can reduce this uncertainty get some handle on the inclination. This paper by Dewan, where they have some modest, by basically fitting the Kilonova data, trying to constrain something about the inclination as well. Now, the inclination in this event was constrained by other electromagnetic data quite strongly, in particular gamma ray emission and X-ray radio afterglows that told us that we were looking at the system, nearly face on or just a little bit off of it. In general, we won't have that information. We may have, since it's pretty highly beamed in one direction, the Kilonova emission is more isotropic and so may give us potentially a different handle on the situation. But with these kind of fits, it's not really clear what about the Kilonova is telling us anything about inclination, how robust or reliable this is. And so the question is kind of what signatures of the system may tell us more. I won't have anything too optimistic to say in general about these questions. I'll kind of describe to you some of the processes and predictions of what we might see. In general, the system is complex and there's a lot of uncertainties and unknowns. And so it's going to be a challenge. There's no magic bullet that I've seen so far that will tell you everything you want to know. But maybe if you put all the data together in some sort of systematic analysis that accounts for all the uncertainties, you can improve these kind of estimates. So let me just tell you a little quickly about the kind of standard story or standard model of what's going on with these Kilonova, and then we'll just see a little bit of how things are different in the black hole neutron star merger. A lot of the physics is similar in both binary neutron star and black hole neutron star. There's just some twists in the geometry and dynamical processes. But the basic idea is one way or another, if you you liberate some neutron star matter from a neutron star in the merger, and you have some neutron-rich gas of neutrons and protons. Eventually, they'll assemble through some alpha process into some heavier seed nuclei with some neutrons left over if it begins out neutron-rich. And then you'll have this process of neutron capture building up to the heaviest elements on the periodic table, and then radioactive decay of those neutrons into protons. Now, the whole process of that building up of heavy elements may take only seconds, a second or so. The radioactive decay can last will be strongest at those early times, and then will decay away, but last for days or weeks, which is what's powering what we've seen. And a lot of work been done on the nucleosynthesis. But the basic factor is that it's largely controlled by how neutron-rich the ejecta is. If it's very neutron-rich, that is a low electron fraction, which also means a low proton fraction. You kind of robustly produced R process distribution that resembles the solar R process distribution. And a lot of the nuclear physics establishes that pattern as opposed to the details of the outflow properties. Lighter elements, less than about a quarter in electron fraction, less than about a quarter of an electron fraction will produce lighter elements. And then the idea is that the radioactive decay of these produce, in the way other radioactive transients like supernova produce some optical infrared emission. Idea proposed by Leah Paczynski. Brian Metzger here worked out, it's contributed to a lot of the fundamental theory all along the way. But the basic idea is you have some heating through radioactive decay of these elements that heats up this big debris cloud. And then it radiates, so the luminosity you expect to see should be related to the mass of material you have times some energy per unit gram per time that you get out of decay, whereas the duration should be related to the time it takes to diffuse out of that optically thick cloud and be related to the mass as well as the opacity. So basically, looking at the height of these events, how bright they are, and their width is giving us constraints on the mass involved. We'll see some of the uncertainties that come from the other complexities and multidimensional behavior of these. And then the last piece of the kind of standard story is that these kind of come in two components, a blue and red component. The heavier elements tend to have lanthanide elements that are very complex in their atomic structure, have high opacity, and so the emission and diffusion time is long. And so you get long emission that's very red or infrared due to the photosphere being much cooler, whereas lighter elements can produce a shorter-lived, bluer emission. Spectral, we expect to see broad spectral features given the high velocity of the ejecta, a few tenths of the speed of light, escape velocity scale from a neutron star. And so models by many people have shown that you can, more or less fit data that were observed for the 2017 event through a combination of a blue and a red component that's superposed to give us, emission that resembles what's observed. The exact location and identification of the features in the spectrum is a matter of ongoing work. It's been claimed by Watson et al. And others that strontium lines from lighter eye process elements may be contributing to dips here. It can also be lanthanides like neodymium or cerium contributing. But the basic idea is simple fits to these observations of the binary neutron star merger suggest something like, 0.05, 0.06 solar masses of material ejected from the system. Now that'll be uncertain by factors of several for a variety of reasons. And the rate of these events will be uncertain, or still uncertain since we don't have a large number of events. But if you put the two together and assume that this is sort of typical and the rates are in the range implied, this is the kind of event that can contribute to a large fraction or all of the R process elements that we see in our galaxy. So is there, what role does does black hole neutron stars have? Do they contribute as well? Will they have similar signatures? And the answer might be that they contribute nothing and that they're really uninteresting and that most of the rest of this talk is not all that relevant. And the reason is that for a large region of the parameter space, in particular high mass ratio, the neutron star can just be swallowed whole by the black hole without liberating any material at all, giving no heavy elements and no Kilonova signal, right? And the basic idea is that the neutron star tidal disruption radius has to be outside of the innermost stable orbit of the black hole. And so, this can be done with detailed calculations, or this is just a plot I made using the simple scaling relation from Francois Foucault, showing that, for a non-spinning black hole and a typical neutron star, a typical radius, if the black hole is more than, 2.5 or 3 solar masses, most of the neutron star is just going to be swallowed whole. Now you increase the spin of the black hole, the innermost stable orbit goes out, and so you may be able to disrupt stars even with a larger black hole, assuming that the orbit is, in the same direction as the spin. And so it may be possible to have larger mass ratios if you had a spinning black hole, although it's not clear that the spins of these black holes will be significant in the first place. Question?
I was wondering if the equation of state of the neutron star matters at all on this plot, if you can shift significantly things within the theoretical uncertainties or not.
Yeah, it does. So the other issue is the radius of the neutron star. This simple parameterization is using the mass as a proxy for some standard assumption about how the radius may change with mass, going to smaller mass, giving you a larger radius and able to be disrupted at the larger mass ratio. But that's but for different, this will be dependent upon the equation of state and how much the radius changes in terms of the mass of the neutron star. So there'll be some range here, which is in a sense, if we see a kilonova emission from one of these systems, of course, it implies there was a neutron star involved, and that the fact that it will have to lie somewhere in this allowed region will tell us something about the spin and potentially the equation of state of the neutron star. So just the detection alone, combined with the LIGO constraints on the mass ratio and otherwise, will be of interest. And the ejection mass, we said there'll be some tidal material that gets flung out. There'll also be a material that falls back and forms a disk around the black hole. And then there can be post-merger evolution of that disk that over larger timescales can eject a large amount of that disk in winds. And that material may be less neutron rich and form less heavy elements due to the neutrino radiation in these hot regions here, which can tend to turn preferentially neutrons into protons, right? So in the neutron star merger events, the tidal ejecta seems to be quite small in these symmetric systems, almost negligible. There may be some material that gets sort of dynamically shot out as the stars come together. But it seems like the most promising way to explain the ejecta seen in the binary neutron star is through largely post-merger winds. Those may be present as well in a black hole neutron star, but for certain parameters, you can get very large amounts of mass, 0.05 solar masses, 0.1 solar masses ejected in the tidal tail. So I'll say more about that since it's really a distinctive feature of the system, right? So this is one simulation of the black hole neutron star merger tidal ejecta. This is for a 5 solar mass black hole with a 1.4 solar mass neutron star. The spin of the black hole is high to make sure that the neutron star got ejected. And the inclination, the orbit, alignment of the orbit was offset from the spin axis of the neutron star, which leads to some qualitative differences. Now you see it has sort of this structure of a thin fan that gets flung out, a very thin structure and large axis ratio, a very strong asymmetry there. That's quite distinct from the kind of disk wind emission you might get from a binary neutron star merger, which will have a more spherical or at least axial symmetric kind of shape. So this is the structure you see sort of immediately following the disruption of the neutron star. It'll be modified in the subsequent evolution of the system, and that's a phase that is not always taken into account. The idea is that as those nuclei that were produced start to decay on a few second timescales, they'll introduce nuclear energy into the system that's not negligible in terms of its dynamics. So this is work by a grad student of mine, Sivadarba, who worked with Francois Foucault's simulation of the merger to carry it out from a few milliseconds after the merger to hundreds of seconds afterwards, before completing sort of the dynamical evolution of the system. And the idea is that as the material starts to expand, it's initially moderately hot, but it'll cool as it expands and loses energy adiabatically if there's no additional heating. But if you include the factors of radioactive heating in that R process event, then you start to heat up the ejecta to larger temperatures before eventually the heat rate falls to the case where the adiabatic cooling starts to dominate again. Right? These are showing different assumed heating rates, which may depend upon the nuclear physics and the electron fraction of those materials. Up at the top is the kinetic energy, which it doesn't change much in this post-merger dynamics, although it does increase a bit due to the extra energy input due to radioactive heating. It initially goes into thermal energy and then serves to basically puff up and accelerate the ejecta. And that effect has some influence on how much, globally, how much kinetic energy and mass winds up getting ejected here. These are distributions from that model showing you the electron fraction and the velocity. The electron fraction is here very low because it's basically just neutron star matter that was torn off of the surface of the star. If you don't include any of the radioactive heating, then some fraction of that material is gravitationally bound and falls back upon the black hole, including heating and also some effective neutrino losses. You get moderately more mass ejected due to this extra acceleration. You also get some shift in the velocity distribution to moderately higher velocities. Right? In total, in this system, up to 5% of a solar mass was ejected in this tidal tail. And so after running it through the general relativistic hydrodynamics simulation to follow the dynamics after the merger itself, that tail has expanded out and puffed up into something larger than the initial flat disk that we saw originally. The heating, radioactive heating at these early times, instead of escaping, goes into pressure and basically puffs this thing up from a thin fan to something that's more like a kidney bean shape. There's still a net asymmetry here, but it's much more mild, only about a factor of, maybe an axis ratio of 2, almost looks like an ellipsoid about an axis ratio of 2. But what's perhaps more interesting is that in addition to this kind of global asymmetry, there's sort of a net motion to the entire ejecta. So the ejecta is expanding out in all directions in a roughly spherical way, but the entire center of mass is moving along at a velocity comparable to that expansion velocity. So velocity about 0.15 c or something here in this direction. That's distinct from typical sorts of transients in supernova where the center of mass is sort of fixed at 0. This is sort of a bullet or a kidney bean bullet that's been shot out in one direction. And that'll have implications for what we see. They're looking from different directions, whether this thing is moving toward us or away from us. And again, distinct from what you might get in a binary neutron star, where we expect to have a more symmetric configuration and no sort of bulk directed motion. I'll say, although I won't talk much about it, but there's a lot to say about it, is that in addition to the tidal material, that material that forms around the black hole in an accretion disk will go through some phase of accretion and lose material in winds, as well as potentially producing relativistic jets. And this has been studied by a number of groups. This was just a recent paper that appeared on the archive by Gottlieb and Sasha Tchaikovsky and others. But a large amount of the mass in this disk, maybe 40% or so of it, will wind up being ejected in winds afterwards. That outflow, at least in these simulations, which include general relativity and magnetohydrodynamics, tend to be aligned along the axis a little bit more and have this sort of prolate symmetry. And also a range in the electron fraction that may be higher than the tidal material and have some angular dependence, being higher in the polar regions and lower towards the equator. That's due to weak interactions that occur more in these lower density polar regions than along the equator. A lot of physics involved in these simulations and a lot of ongoing work to improve the treatment of those weak interactions and the neutrino transport and to improve the quantitative accuracy of these kind of simulations. But generically, you see things somewhat like this. And those two only follow the dynamics out for a few seconds. As that material evolves, again, it will be dynamically modified by the radioactive heating that follows in the subsequent minutes. And so this is work by another Berkeley graduate student, Hannah Klein, who took the simulations, this previous GRMHD simulation, and continued them out until they reached a phase where the pressure was negligible and the dynamics basically became coasting. And the final ejecta structure, again, has some asymmetry, as sort of a prolate type asymmetry with some compositional variation as you go from the pole. And the velocity was modified due to heating in a similar way we discussed, that the initial ejecta here was rather slow from the disk, maybe 0.05 C, accelerated by the radioactive heating up to about 0.1 C. In this case, leaving behind actually not much material in the low velocity regions, although it's a little uncertain whether the post-merger phase has really captured all that marginally bound material that may fit into this system. Well, what do these look like when you model their light curve? So this is radiation transport simulations done by Siva using in this case, just the tidal tail ejecta, not the disk wind material, and showing the bolometric light curve you expect to see from the Kilonova as a function of time, basically for a number of different viewing angles of that system. And as might be expected, given the large asymmetry that you saw, there's a big variation. There's anisotropic luminosity, variation of factors of 2 or 3 in the peak brightness of this, which tend to converge a little bit at later times. Yeah, question.
Is there anything preventing these models from being, I guess, trustable if they're pushing back to earlier times?
Then back to these earlier epochs.
Yeah, like
20 minutes. Yeah, some of these calculations can be carried out. They become computationally more expensive as you go back in earlier in times. And our uncertainty and sort of the opacity of material at these weird materials at high temperature becomes more uncertain. But you can also make predictions at the earliest epochs when things are hot. Yeah. Yeah, question.
Sorry, I should do a follow-up question. What was the earliest spectrum or earliest detection of? I think it's a day later or something like this, right?
Yeah, about a half a day.
So do you believe 20 minutes is possible?
Yeah, sure.
It could have been done earlier had fortune been right in the timing of where the event was in the sky, what facilities were available. But that was a special case where it was easy to find the counterpart. As I kind of showed in the first plot, there can be a wide air circle in the sky, and it can take a while to find the right counterpart if it's not as nearby as the 2017 event. So this can be kind of complicated to try to understand what's the effects driving these variations. It implies that just naively using a 1D model to fit data can result in mass estimates that are wrong by factors of a couple, 2 or 3. Despite the complexity, you can basically, we found, break it down into 2 physical effects that drive the variation in luminosity with viewing angle. The first is that, at least at these later times, around peak, where radiation has been able to diffuse through the bulk of the ejecta, it can roughly be approximated by thermal emission from the surface of the ejecta, basically a near constant temperature black body, which means the emission should just scale like the projected surface area of that system. And so, for example, for a perfect oblate ellipsoid, you can write down analytically what the projected surface area is as a function of the viewing angle, and write the luminosity as some function that depends on that projected surface area and evolves with time. And then these dashed lines are just analytic, simple models like this that show that they capture, for at least these simple, idealized, in this case, an ellipsoidal geometry, fairly well the effect. And one thing you notice here is that there's more dispersion at earlier times near peak than at later times. And that's because as you go later and later, eventually you become optically thin, and the system will head towards being isotropic, where the emission is equal in all directions if there's no bulk velocity. And so already coming to this question of can we constrain the inclination of the system in any way? Well, one thing that pops out is maybe some measure of the variation, this decline rate variation in sort of the peak luminosity to some luminosity on the tail. It's just showing you, another way of visualizing. In this case, for the actual 3D black hole neutron star merger, I showed you how it varies as you move around due to this projected surface area effect. So we saw I had sort of a kidney bean shape of axis ratio of 2 or so. And so the sort of analytic approximation describes fairly well its brightness variation as you go from face on to edge on, but with some variation as you change the phi angle as well in a more complicated way. So basically, that projected surface area captures well, at least one factor that it leads to its anisotropy, which is a useful rule of thumb. It just tells you that you can easily estimate how big the effects will be and how much you have to modify your expectations by analyzing the bulk geometry of the ejecta itself. Here, kind of showing you whether that peak to tail ratio, which seems apparent in sort of simplified models, is actually effective at being an indicator of inclination. There is some mapping here between this measure of the ratio from the luminosity at peak to the luminosity 5 days later, along with the, in this case, the angle relative to the orbital direction. But it's not a very strong effect, varying only from 2.4 down to 2.0. And it also depends upon the phi angle due to complexities that I'll talk about in a second. Moreover, it's degenerate with other effects. For example, the radioactive heating rate, which is fixed in that one model, but for different ejecta may vary by some significant factor due to the production of different elements with different heating rates and lifetimes. This is just showing you for nuclear reaction network calculations of the heating rate for different values of this electron fraction, which can show a spread at late times as well. And the fraction of this radioactive energy that actually gets deposited and thermalized in the ejecta and is re-radiated as optical infrared light can vary as well with the conditions of the ejecta. So there's other factors that may influence this decline rate, this peak to tail ratio. There's information there about the inclination, but it's not in itself going to tell you what the value is. The other physical effect that's influencing the luminosity you see from these systems is this bulk directed velocity that I mentioned, that the entire system's moving in one direction at some significant velocity. This is just a simple, relativistic Doppler boosting, where the luminosity, given the fact that the energy is going to be boosted and the system is coming towards you, as well as slightly beamed towards you, should go like the square of this this Doppler factor, right? And so for the velocity that we see here, about 0.15 c, viewing along the velocity with the systems coming towards you should lead to luminosities that are a factor of 2 or more brighter than viewing from a system that's moving away from you. So if you sit on the equator and you fly around this thing, you'll see the luminosity at peak rise and fall by a factor of 2 or so. Again, the analytic sort of approximation of the effect is a reasonable approximation of it. So we have a sense of what the system, due to asymmetries, will do as you look at it from different viewing angles. It certainly needs to be taken into account when you're trying to do detailed fitting and estimate the masses involved. But there doesn't seem to be enough information in itself to extract exactly what the geometry is or what the inclination is. There'll also be effects on the color and the spectrum here, just showing you calculations of that model in the radio transfer models of the continuum spectrum. again, the same Doppler boosting effect leads to a shift in the peak of the emission towards the blue when the system is coming towards you, as well as being brighter. And that means that, although it's only a factor of 2 variation in brightness at peak, which is, at the maybe around 1 micron, in the optical wavelengths where you're on this, wean tail of the black body distribution and there's exponential sensitivity, the Doppler boosting effects actually have a pretty significant influence on the emission. And so you can see that if you construct broadband light curves here, in infrared wavelengths, there's, some modest variation in the brightness as you look at it from different angles, but in the B band, can be as large as, 4 or so magnitudes in brightness, depending upon whether the system's moving towards you or away from you. And so that's significant, given that, well, if you have optical wavelengths trying to constrain the amount of ejecta based on non-detections, will be highly sensitive to your assumed orientation. There's other subtle radiation transfer effects that affect things, particularly at early times. Here's a calculation that's going to earlier times. In this case, it's a spherical model, but it's showing you the general effect that at the earliest times, you're really just seeing emission from the thinnest, outermost layers of ejecta. And how steep that ejecta is actually is quite important to how bright things are in the UV and B bands. If it's very steep, you can sort of form a hot surface and get a bluer emission. Whereas if it's more shallow in the density profile, well, there'll be material above the photosphere, even a very small amount of material, which will have strong line opacity that will blanket out the brighter bands. And so these effects of that I talked about before of the expansion phase, where you have radioactive heating kind of inflating the system, can be quite significant. I mean, in the original black hole neutron star merger, there was sort of a sharp cutoff in the amount of mass above about 0.3 C. In the original system, since you proved material off a neutron star with a rather sharp surface, and run with just the original structure, this can lead to some bluer emission because you've sort of formed this very hot, sharp surface. And so some earlier works have suggested that you might have blue emission from black hole neutron stars, but the inflation of the system and the radioactive heating tends to sort of smooth out that material at the outer edge by having pressure gradients drive this out. Again, there's some uncertainty in how well these numerical simulations capture the small amount of mass at large radius and what the dynamics are there afterwards. And there could be interesting additional heating mechanisms, which Brian's discussed about whether if it's very neutron rich, you might have pure, free neutrons in the material at the highest velocity that would decay on the neutron decay time scale about 15 minutes and lead to additional heating at the various earliest times. But again, how bright that is probably rather sensitive to the density profile out there, which is hard to constrain. In addition to the color continuum of the spectrum, we can look at line features, which actually do provide somewhat more diagnostic power. This is a somewhat simplified model of that black hole neutron star tidal tail here, which we've added in addition to continuum, kind of an individual strong line feature to kind of highlight the kinematic effects on the spectrum. And again, you see what you might be anticipated, that when the system is coming basically at you, you see a large Doppler shift in the overall position of this feature at 0.3 C, whereas if the system 180 degrees from that, the Doppler shift is not quite as significant. And both the position of the minimum and the peak shifts as well. So the potential effect to kinematically see whether the system is coming towards you or receding from you. one of the uncertainties is we still don't have a good handle on what the spectral line features are that really dominate the kilonova spectrum. There's some suggested lines that might be strong, but in general, it might be hard to distinguish whether you're seeing here, the same line Doppler shifted by a large effect due to the orientation of the system, or if it's just different line features altogether coming in. So a single event's probably not going to totally answer the questions we have, but with better understanding of the spectral lines that make up the system and a larger sample of objects, we may be able to disentangle some of the geometry of the system through spectral analysis. And then the last thing I wanted to discuss a bit was whether observations of the polarization of the light from this kilonova could give us any additional information, since this is one of the direct ways you can try to measure the asymmetry of the system. Scattering of the light by electrons in the debris can polarize the light. If it's a spherical or circularly symmetric distribution, that polarization will cancel. But if there's some net asymmetry here, you can observe some net polarization in the continuum of the system. That polarization angle may vary with time. At early times, when the system is very optically thick, radiation will preferentially diffuse out, in this case, in the polar regions where the optical depth and distance to the surface is less, leading to a net horizontal polarization. Where at later times, or when the system's starting to become optically thin and things are diffusing out, and generally you'll sort of see emission from the entire system, and you'll get more polarization in the vertical direction. So we can do, again, kind of generic calculations of the polarization of a transient. In this case, it's just a pure electron scattering debris cloud that we're considering with an ellipsoidal geometry to see the generic effect, what this polarization level would be over time for different axis ratios of that ellipsoid. And we see this effect that at early times the polarization is negative, which in this context means horizontal. It rises and crosses zero, and then it flips signs as radiation starts diffusing in the perpendicular direction, and then reaches a peak sort of around the time that the system begins to become optically thin. The degree of polarization can be up to a few percent for ellipsoids of axis ratio of 2 or so. But this is, of course, orientation dependent. This is sort of the maximum polarization you would see if you observe this thing. In this case, as an oblate ellipsoid observed edge on. As you observe from other orientations, the polarization the level will vary by sort of a cosine squared type function as the system becomes, circularly symmetric when you view it face on. Right? Yeah.
Maybe you're going to say this, but how does this change? I mean, electron scattering is, of course, not the dominant opacity, except maybe blue. So is this so? But how do you think this would change other sources of opacity? Is there sort of way to maybe scale it down?
Yeah, I'll say that in a second. Yeah, well, it's a good point. That this is just assuming that we have pure electron scattering and not accounting for the line opacity as well. There were calculations, or actually observations. Well, there have been previous calculations of polarizations in this Kilonova context by Bull et al. It finds kind of similar values. And there were observations for GW 1708-17 that measured polarization in the continuum of something about 0.5%. It's unclear whether that polarization is sort of intrinsic to the system or is just polarized by, dust scattering along the line of sight. So more polarization, and particularly a time-dependent polarization that would actually see this evolution of the polarization in the expected fashion would be better for constraining the geometry. but yeah, you see that naively, if this was a pure electron scattering system, this would constrain it to be either quite symmetric or a viewing angle inclination close to face on. But there is a strong depolarization due to line opacity. So electron scattering opacity is actually subdominant opacity in these mediums. And the lines, as far as I understand, will tend to depolarize the light and subtract this effect. And so again, when you have the heavy R process elements and these lanthanide species involved, the opacities are quite large. The ratio of line opacity electron scattering can be, a factor of 100 or more or greater. And in this case, you'd expect that essentially the entire polarization signal will be destroyed by depolarization by interaction with lines. If you do have some lanthanide poor material, lighter R process, then if you go far enough into the infrared, at some point the electron scattering starts to become comparable to the lines. So this again is sort of pessimistic for using this as a powerful diagnostic of the geometry and inclination of the system. Is for the tidal tail, which is thought to be potentially very heavy R process because it's very neutron-rich material. The signal may be killed, but if we do see some emission, a polarization signal, it would signal potentially lighter R process. And again, I mentioned before that there, in addition to tidal ejecta, there may be disk wind material that comes out in the sort of polar regions. And that can lead to other effects. I don't have actually the simulation with the tidal tail ejecta with me right now, but this is just an older simulation showing lighter R process blue emission surrounded by sort of dynamical ejecta of heavier R process. And showing that for certain viewing angles, you'll be able to see blue emission and potentially polarization signals, whereas for other angles, the heavy R process high opacity material will obscure that disk wind material. So this ratio of the colors, again, could give us some inclination information if we were certain of the geometry and the masses of the different components. But in general, be degenerate with other topics. So some takeaways, well, black hole neutron stars, in some cases, there may be no ejected mass and there's no electromagnetic signature to see. But depending on the mass ratio, you might be able to see a significant tidal tail emission and potentially disk winds in some combination. And seeing that would then give you some constraint on the fact that you've seen a neutron star in the system. One of the systems is a neutron star, and may give you some information on the spin of the black hole and the radius of the neutron star then required to lead to the inferred amount of our process ejecta. We see mostly a large amount of tidal material can be ejected, and that's neutron rich, so likely we expect to see red R process emission. But we see for certain viewing angles, there can be a boost in the optical emission. And it may actually be detectable or some chance of detection if the orientation is favorable. It may depend upon certain details of the system, and in particular its orientation and the structure of the ejecta at the very outermost layers. This directed bulk motion of the ejecta and the tidal material is maybe the one distinct feature I can see of the black hole neutron stars versus the binary neutron stars. It has certain important effects on the light curve emission and colors and whatnot. Maybe the most diagnostic feature is spectral feature shifts. And then polarization signatures are probably unlikely to be detected in tidal ejecta, but if there's some component of lighter R process material, and we can get our infrared observations, we might have some handle on that, although it's difficult given the low polarization levels and the fact that it's harder to observe in the infrared. So again, as promised, there doesn't seem to be a smoking gun that sort of answers all the questions, but you can kind of see the landscape of different signals and diagnostics that are available, and with comprehensive modeling that sort of accounts for all these effects that we're sort of in a position to do now, and a sample of observed events, which maybe we'll have in the coming decades. Perhaps some clever analysis of those systems compared to the model predictions will be able to constrain to higher accuracy the masses involved, the orientations, and the other features of the system. So yeah, I'll stop there and take questions.
Thank you very much for the very interesting talk. So first, do we have any questions from Zoom? We'll just give people a moment. Or from the room, for that matter. Yeah, Brian.
Thanks for the nice talk, Dan. I guess
I don't
Yes,
know, but,
please.
okay. I guess I was going to ask you a little bit about nebular diagnostics. So when we get to the nebular phase, if we're so fortunate to point JWST there and there's a lot of infrared line emission, should we learn anything from the shapes of the lines, or are these Doppler effects just going to wipe out any difference between an axisymmetric and one-sided ejecta, for instance?
Yeah, that's a good question. If we can observe late enough that we see the system when it's in a completely transparent phase, which may be weeks after the merger, we're not quite sure what we'll see yet. It depends on sort of the emission properties of these elements. But comparing to supernova, where you see sort of dominant lines giving sort of broad emission features, then there would be some diagnostic, potentially powerful diagnostic of these bulk asymmetry effects. So if you had something that was, centrally expanding, you might expect to see features that were sort of symmetric around the rest wavelength of the line, or complex of lines that are reducing the emission. But if there's a net bulk motion, then that entire peak of emission in that line complex will be shifted depending upon your viewing angle. Again, the complexity is we don't know very well what the lines that are going to be relevant at those phases, and all the non-equilibrium physics that goes into sort of modeling that phase. But I think it'll be kind of comparable to what I said about the earlier phase, where if you would see sort of net Doppler shift effects, this time in emission instead of absorption, which would give you some diagnostic of sort of the basically the emission profile across this nebula.
I think for a really awesome talk. I wanted to ask about the relationship between, in your head, between the constraining power of the inclination constraining power of the kilonova versus the afterglow. It seemed from what I took away from your talk that you're saying that the kilonova has the most constraining power on the inclination at small inclinations, which is also, but then your argument seemed for the why we need the kilonova and not use the afterglow, because the afterglow can only be used at low inclinations. So I guess I'm trying to understand what's the scenario where the given how strong the constraining power for inclination is from the afterglow, what's the scenario where the kilonova helps you appreciably? I must have missed that.
Yeah, maybe I wasn't so clear. I think that the afterglow is going to be more powerful when you can observe it, because you have sort of stronger asymmetry of the system, a stronger jetted material, and so you can, the variation of the luminosity is a much stronger function of the inclination angle. and the physics, at least the way it's modeled, is simpler um, to try to diagnose how the light curve in those spans will depend upon uh, the parameters, as well as in some cases like in the 2017 event, they could actually resolve jet structure in the radio. And so if that's all possible, then I think that's your best bet. But the question is, in general, things are farther away. It'll be hard to detect those, gamma ray bursts and um, afterglow signatures, unless you're really pretty close to on axis. So you may be limited to a small range where you'll have a very good handle on the inclination. And the question is, the more general case where you have something that's larger, more significantly off axis, can you do anything to constrain it from the kilonova itself? And I'm not so optimistic that's easily done given all the degeneracies that we've seen. There's information there, but whether you can sort of isolate it in a clean way from the kilonova data, I think is a challenge. But.
Yeah, just a quick follow-up. So that makes a lot of sense. I guess what I was looking at in your slides, again, seemed to show that most of the power for inclination constraint comes at lower inclinations from the kilonova. So I guess the question is, would a non-detection of the GRB or the afterglow constrain your inclination better or worse than the amount of constraining power you have on the inclination from the kilonova at higher inclination angles? Is that?
Yeah, non-detection. Well, I guess there have to be some theoretical assumption there that in terms of the jet being produced and the energy of that jet, if there's no appreciable energy in a jet, then that could be you could still be looking nearly face on, or at least slightly off of face on, and miss a signal. So you might if you had theoretical motivation to presuppose some jet power in the system, the non-detection would tell you at least some sense in which you were off axis. But.